Dr. Sara Casciati from University, Catania. Dr. Casciati, please.
Calibration on experimental data, and estimates of the tension in the stays will be derived, and their effects on the model features of the deck of the bridge will be investigated by model analysis. Then we will perform nonlinear large strain dynamic finite element analysis under pedestrian crossing. This will require the strategy in order to model the human-induced loading of a group of few persons, not a crowd loads like you usually see in literature. Then the simulation of the recorded response, the results of this analysis, will be assessed with particular focus on identifying the tension in the cable time histories, which varies under each pedestrian crossing. This is in view of implementing a control strategy of the tension in the cables, which is variable with time as the pedestrian crosses the bridge. So the motivations for these studies are motivated as necessary steps in order to investigate the problem of quantifying the possibility of counteracting the tension degradation in the cables during the serviceability condition, which means away from the resonant regions, and implementing a low-cost control law, because we are dealing with a toy bridge compared to real actual cable stay bridge. It's a footbridge of 100-meter spans with only a few cables. So the control solution needs to be affordable. The cost of the control needs to be less than the cost of the bridge itself, of course. So we will implement the control only on few cables, which are the main external ones. But this is still a feasibility study toward this final outcome that we will discuss in the end as a future research goal. So this footbridge is quite slender. It reaches a span higher than 100 meters by exploiting technologies based on the combination of glued timber laminated deck and steel elements. The finite element model was implemented in the software MARC, which is particularly suitable to carry out nonlinear dynamic analysis in large strain with an updated Lagrangian description algorithm implemented. But of course, the finite element modeling assumptions are subjected to large uncertainties. So in order to have a realistic and reliable finite element model, we had to calibrate it based on experimental data, which were taken using a limited amount of sensors. There are 3-axial accelerometer monitoring the deck response and uniaxial ones placed on the main cable next to the mid-spans, where the displacement of the deck are expected to be maximum. We want to focus on the deck response because, of course, the final target is provide comfort to the users during serviceability conditions. So measurements were taken under pedestrian crossing. Those measurements, both on the deck and on the main cable in the direction direction y, which is transversal, and vertical, were processes first by simple Fourier analysis of the frequency content, and then the results were confirmed by giving these signals as input to a software that performs experimental model analysis based on data-driven subspace identification method, and it provides not only the frequencies but also the mode shapes and the associated damping, based on which we calibrated our finite element model. Once the finite element model was calibrated, we also, in the modeling phase of the process, assigned the tension to the cable. The construction procedure followed to actually build the bridge inspired the procedure for assigning the tension to the cables. Indeed, first the gravity was given without the central beam element being mounted. Then the elongation of the external cables was applied. The central mid-span beam elements was mounted, and only in the end the gravity was added to all the cables in order to reach the initial configuration. And the static sags were computed. At the end of this process, we estimated the tension in the cable, and we compared the results with the many empirical formulas that are available in literature in order to approximate the relationship between the tension in the cables and the frequency, experimental frequency of the cable, accounting for both the sag extensibility and the bending stiffness effects. Furthermore, using a finite element approach, we can also consider the spatial variability of the tension along the cable. So these results were confirmed by this empirical formula. Once our model is calibrated on both the experimental data and the formulas, we analyzed the mode shapes. There were many mode shapes because the cable's mode shapes were mixed with the deck mode shapes. So in order to identify which one are representative of the response of the deck, we compare the numerically obtained mode shape of the deck with the one obtained by experimental model analysis. And here it's easy to identify which one are mostly in the out-of-plane modes and which one are the in-plane modes. And the comparison between the numerical model features of the deck and the one of experimentally identified. Now, once our bridge has been calibrated, let's preliminarily investigate the effects of varying the tension in the cable on the response of the deck. We say we want an economical solution, so we're varying the tension only by elongating the external cables only. Of course, elongating the external cables only causes a redistribution of the forces in the other cables. And we want to make sure that the redistribution of the forces in the other cable turns out to be of a beneficial effect on the deck response. In order to do that, we recalculated the modal features with different initial conditions as the tensions in the cable. And we see that the effect of increasing the tension in the cable causes an increase of the lower modes frequencies, but the higher modes ones remain unvaried. So we only affect the lower modes by increasing their frequencies. Now, this was the static preliminary part. We moved to dynamic analysis, but in order to carry out the dynamic analysis based on our experimental results, the modeling of the human-induced loading needs to be discussed. As mentioned, in literature you can find many models that are targeted and very detailed in modeling the walking of a single pedestrian, or the crowd load due to the lock-in phenomenon, which is very well known. But few studies, actually I didn't find any, study what happens when you consider a group of few persons, like a group of 6 persons. This configuration is of interest to our bridge because it moves at a frequency, it excites a frequency of 1 Hertz, and our bridge frequency is 1.3 Hertz. So the common strategy to model pedestrian loading is to adopt what we already know from wind engineering. So use a stochastic procedure that is similar to the one adopted for wind. What is the difference? When you deal with wind engineering, the surface interest by the wind always stays the same, remains the same during the analysis. Instead, when you consider pedestrian crossing, the interested grids of nodes moves along the deck at the speed of the pedestrian crossing. So we have to model also this effect. The modeling of the actions are carried out in 3 steps. First, we carry out a stochastic simulation in order to acquire realization of a special random field at given time steps. These realizations are then used to reconstruct the time history at each node of the grid. And in the end, these time history are given as input to the finite element analysis. To model the stochastic random field, of course, several assumptions needs to be introduced. Essentially, the force in the both in the transversal and in the vertical direction of the bridge induced by the pedestrian modeling is consists of 2 parts. First, stationary part, which is the equivalent of the wind average speed, and a stochastic component, which instead is modeling, simulated using classical weighted amplitude wave superposition back from the 80s, proposed by Shinozuka and Diodatis, which is based on the Cholesky decomposition of the spectral matrix. The spectral matrix, which takes into account for the fluctuation and the exponential decay of each single trajectory. In order to model the autospectra, we used the expression proposed in the model by Solari and Picardo to model turbulence, gas turbulence in wind engineering, with the parameters calibrated, of course, on our experimental data. And those are the autospectra that results from this calibration. At the end, after the Cholesky decomposition, we go apply a deterministic shape function, which instead takes into account of the spatial constraints. So, for example, that a part of it is a shape function, a part of it takes into account that the pedestrian needs to walk away from the borders, and the other part of it that the pedestrian needs to keep a distance between each other. In the same way, in wind engineer, they consider the variation of the wind with the height. Here we vary along the surface. So those are examples of several realizations at different time step, at different time interval. From this realization, we model the transit of the group of pedestrians into our grids of nodes during different phases of the transit. So, for example, this is the entrance. Here we have 4 pedestrians in the grid, and here is the different phase of a complete transfer from the entering, all of the pedestrian in the grid, and here the exiting process. We assign the resulting time histories to the nodes of the deck, and these are the time histories that in different nodes, the nodes of the grids undergo during the pedestrian crossing. So, for example, this is the entering process, the exiting process, and here is all the 6 pedestrians in the grids. There are different pictures at different timings. So now let's analyze the results of this nonlinear dynamic analysis in terms of the acceleration and displacement response of the deck in both the transversal and the vertical direction. Here there is, we compare nodes 72 and 29. 72 is the midspan, and 29 is approaching the midspan. So you can see how it varies with time. There is, I didn't take away the mean value of the signal in order to plot them together. Now let's vary the initial condition, because in the end our task is to vary the tension in the cable. So what is the effect of assigning more or less tension to the cable? The less tension would be the tension degradation effect. Here again we plot the displacements at midspans, but the attention is particularly focused on the time history during the pedestrian crossing of the tension of the cable, because the tension of the cable determines the stiffness of the structure. The stiffness in the structures varies the structure of the space matrix. So the space matrix that will influence our control laws is not constant in time, but it varies as the pedestrian crosses the bridges. So we need to know how the tensions vary to know how the state space matrix also varies and is an eigenstructure to perform the control. So here we obtain the different time history of the tension. You can see in blue the initial condition, and the tension force. It's either increased to simulate the actuating effect, or decreased to simulate the deterioration effect. This the frequency content of the response of the deck. We want to know how does it affect the dynamic of our bridge, this tension increase or decrease. With our results right now, we can see it on the spectrum, on the frequency content of the response of the cables. So if instead of considering the midspan of the deck, we consider the stay cable, we can see that the part affected by the pedestrian crossing is the one around 1 Hertz. And when we assign additional elongation to the cable, these peaks are smoothed. If instead the tension in this cable is deteriorated, these peaks are more pronounced. Now it's a matter of better calibrating our pedestrian-induced loading in order to better agree the obtained response to the one that was experimental measured. The final task, but this is only because the beginning of future research, is only the final test, so don't ask me for results, is, as said, we characterize the time dependency of the tension during the pedestrian crossing. This affects the stiffness, it affects the time variability of the A matrix in the state space representation. The next step will be to write the state space equation on a reduced order model and to apply a control law. And the two approaches that we are in mind, we either resort to a piecewise linearized approach or a completely nonlinear approach, which probably is going to be easier, using a fuzzy law. And right now, this is where we are in our ongoing studies. Thank you very much for the attention.
Sara, what is the reason for this study? Are you trying to support designers of this bridge? Because if this is
no, it's the problem statement at the beginning. Let me go back there.
I probably lost it somehow.
Yeah, at the initial slides, I wanted to collocate myself and the objective of this control. And as say, we want to counteract the effect of natural deterioration with time of the tension in the cables without going into resonant regions, but staying under serviceability condition of the bridge.
Okay, that my question comes. Do you consider the worst case scenarios? Because you use the basically models of the pedestrian going through, and you could imagine that people walk or people jog. It's very different, basically, dynamic footprint on the.
Yes, indeed, during the experimental. Oh, I'm sorry.
Yeah.
Finish.
So the question is something in your procedure, do you consider the worst case scenario? Because that is where you will get.
Exactly. During the experimental campaign, we did excite the bridge using different configurations. So we had the single pedestrian running, the single pedestrian jumping, we didn't do vandal load, but all the rest we tried. And this configuration was the one hertz that was the one more close to the 1.3 hertz that we find from the experimental model analysis study. Thank you.
Okay, any other questions? Yes, any question? No, okay. Okay, if no more questions, please join me to thank Dr. Casciati again. Thank you.
Thank you very much.